Um, Hi all. In this section, we are going to learn about one of the major applications of integrals. So what we call area between curves. Area between curves. Okay, so this is an extension of the definite integral. So we know that the definite integral, which defines an area. So the definite integral. When we look at the definite integral, when we have a b fx dx, so this is an area. So we know that if you have a curve, we assume that which is positive, and then let's say a and b we have over there. So what's going to happen, this integral represent the area between these the curve and the above the x-axis. That's very important, above the x-axis. So this is y equal fx curve. So what we're trying to do, we're going to extend this idea for a general case. For example, let's look at this situation. So let's say we have two curves. So we have one curve going like that I'm going to call y equal fx, and let's say there's another curve going like this. So this is y equal gx. Okay, so the goal is to let's say find the area between the value of x a and the value b, that's x value b. So let's say we want to find this area. So that means what area we are looking for? We are looking for this area bounded by those two curves and the two vertical lines, x equal a. So that line is x equal a line, this line is x equal b line. Okay, so the two curves on x equal a and x equal b line. So what we're trying to do, it's as we did before, remember, like in when we have this is a single area problem, what we did, we draw approximate rectangles, right? And then we find the area of the rectangle and then we add them. So we do the same thing here. So even in this situation, so what's going to happen, so we're going to have, so let's say, so I'm going to grab this again, just taking unnecessary things out. So we have, so that's the top curve and that's the bottom curve. So what we're going to do, so that's the area in between. So that's what we're trying to find between a and b. So what we do is we can strip this into small rectangles. So that's the idea. So we can strip this into small rectangles like that. So those are the rectangles. So we pretty much pick the middle point because that's kind of better approximation. So pick the middle point. I mean, in general we can pick any point, so it doesn't really matter, because when you have a lot of rectangles, it's going to approximate the area. So we pick the middle point of each interval and then draw the approximate rectangle like that. Okay, so that's what happened. So let's say so we're going to pick a point inside each rectangle, the x value. So that x value, that what we normally call the x star. So that's the x value. So that's x star value in that rectangle, and then the height. So be careful here. So the height would be the difference in the y coordinate. So you can see, so for example here the height would be this whole length. So that's the height. So that means so what is that? So that is the this we normally call y equal fx function. So this is the other one is y equal gx function. So that means the height of the rectangle going to be the top minus the bottom, right? So it is f x star, that's the top function, and then subtract the bottom function, which is gx star. So those are the two functions. Okay, so we have the height, the top and the bottom function. Okay, always, because then you get like a positive area. So now you can see that this is positive. So that's why we do it, or 0 if they are equal. So that's the kind of idea. It's always the top minus the bottom. And then we have the equation. So the equation going to be now, so if you write this as a limit, so what's going to happen? So the area which is approximated by by the sigma. So let's say we can strip this into n rectangles. So if we have n rectangles, so what's gonna happen, we have the first 1 through n, all the rectangles, and the area of one rectangle is height times the width. So the height is fx star. So you can say if you need the ith one, you can say xi star, because it's much relevant here. So then you can consider everything. So I'm going to say this is the ith one. Okay, so xi star minus g I star, and then multiply by the width. We can say we can strip into equally with rectangles, so it's going to be delta x. You don't need that, but it's much easier. So delta is the width, and then so that is the area of one such rectangle. Okay, area of one rectangle, area of one rectangle. Now what we're going to do, we're going to divide this into a lot of parts, or simply we're going to send n to infinity. When you send n to infinity, you're going to get the equality here. So that means so what happened when you send n to infinity, it's going to be the area. So the limit n goes to infinity. Now we know that you can write this as an integral, because this is the integral. So what integral? So so that means your area going to be the integral. The starting value is a, ending value is b, f x minus gx, and then dx. Okay, delta x becomes gx. So that is the area formula. So this is always the so what you want to remember is the first one is the top, and the other one is the bottom, so that it's always positive. That's why we choose it like that. So it's gonna get a positive answer for that. So that's the formula. Okay, that's the only formula. And when we do problems, you want to make sure that you're gonna pick them right, the top and bottom, so that you get a positive answer for this. Okay, so the assumption here is we assume that fx is greater than or equal gx. Okay, so let's do some examples now. So so the first one, so let's do like something like, you know, easy first. How about this one? So let's say find the area bounded by the curves. Find the area bounded by the curves y equal ex, y equal x, and then let's say x equals 0 and x equal 1. So there are like a bunch of curves here. So the best thing would be let's graph them. So it's kind of give you an idea. So like that's always a good practice to graph them and see the situation here. So what we have, so we have y equal ex, and so y equal ex is going like that, and it's gonna go like this. So that's y equal ex, and then we have y equal x. So y equal x is the line going like that, and then we have 0, and then we have 1 here. So x equals 0 is here, so that's the x equals 0 line. So this is the x equals 0 line. So this is y equal ex, this is y equal x, and this is x equal 1 line. So this is x equal 1, x equal 1. Okay, so that means the area they are talking about is the one here. So that's the area we need to find. And you can see that without calculus there's no way we can find this area, because these lines are not straight lines. these curves are not straight lines, so there's a problem here. So that means we need to use calculus for that. Okay, so what we do, we're gonna look at the typical rectangle here. So let's draw one such rectangle. So that's the typical rectangle. So and that is the delta x we are talking about. That's the gap, delta x gap. So that is the xth position here. So that's the x1, x value. So now what we need is the height. So what's the height now? So height is, so you can say that's the height. It is y, the top value, minus y, the bottom value. So right, y the top value minus y the bottom value. So what are these? So in this case, you're gonna get the top value is ex, and the bottom value is x. So you substitute from x. Okay, you substitute from x. Now we can find the area of the rectangle. That's not that difficult to find because we know the height and the width. So that means your integral now becomes, so the area equal the integral a to b fx minus gx, so the top and bottom, and dx. So this is the top and the bottom. So we can plug in. So it's going to be, what are the limits? Go from 0, limits of x, because x is changing. X is the one changing. So x changes from 0 to 1. So 0 to 1, 0 and the 1. Those are the limits of x. And the top function. The top function is, so it is yt minus yb dx. So it is 0, 1. Yt, the top function is ex. The bottom function is x. Okay, so the top function and the bottom function. So and then integrate dx. Okay, so that's the integral. That's the integral representing area. So we can finalize this. So it is ex integral is ex. We can find the antiderivative here. So this is x squared over 2, and then we can evaluate this between 1 and 0. So if you plug in 1, you're going to get e minus 1/2, and then if you plug in 0, it is e to the 0 minus 0. E to 0 is 1, so you're going to get e minus 1/2 minus 1, which is e minus 3/2, e minus 3/2 unit area. Okay, so that is the area of the region that's enclosed by those 4 curves. Okay, so let's do another problem. So how about this one? So we have, so find the area bounded by the parabola y equal x squared and parabolas, you can say parabolas y equal x squared and y equal 2x minus x squared. So these are two parabolas. What is the shape of them? So there are a few things to understand here. We know y equal x squared. Y equal x squared has the shapes. It's always like geometry helps you. So this has this is that. It's going to go like that and go like this. So that's the parabola, y equal x squared. What about this one? This one you can factor if you take x out, which is 2 minus x. So what's going to happen? we have 0 and a 2, because this is going to give you 2, x equal 2, this is going to be x equal 0, so that means at those places it's going to be 0, but this is concave down, not concave up, concave down because of the negative sign, so that means it's going to go like this. So that's the parabola, that's that one, the second one. Okay, so now what we want to find, we want to find the area enclosed by these two, enclosed by these two. So that means if you draw the other one here, so what's gonna happen, it's gonna go like this. So they cross each other, so what we are looking for is this area. So right, we are looking for this area. Now there's one additional problem here. We don't know the limit, because we know the starting value 0, but we don't know the ending value, so we also need to find this ending value, the b value. Okay, so those are the few things. So what you do if you get a problem like that, first try to draw the graphs, and then try to find the intersection points. Okay, intersection points. Okay, so let's continue the problem. So we have so I'm gonna draw it here again. So we have one going like that, and we have another one going like this. Okay, those are the two curves. So this is y equal x squared, this is y equal 2x minus x squared, and then what's can happen, this is 0 and this is this we don't know. So let's try to find out what the exact value is. Okay, so what you're looking for is this area. So we are looking for this area. So that's the area we are looking for. Okay, so so for the intersection point, so for the intersection point, for the intersection points, what we do, we set them equal, because we know that at that point the y coordinate are the same, so we set them equal. So we're going to say x squared equal 2x minus x squared. So that's the first step, you set them equal, and then solve. So you can bring them to one side. So if you bring them to one side is 2x squared minus 2x equals 0. You can divide this one by 2, so you're going to get x squared minus x equals 0. And then this has factors x minus 1, so this gonna give you that x equals 0 and x equal 1. So those are the intersection points. These are the intersection points, the x value of the intersection point. And so if you need the y value of the intersection point, just plug into one of the curve, then you can find it. But in this case you don't need, you only need the x value, so that means this is 1. So the intersection point here is 1. Now what you want to do is to find the height of the rectangle. So it's very easy to find, because geometry tells you that what's the top curve and what's the bottom curve. So that means the area is the integral going from a to b, fx minus gx. That's how we normally write the formula. So it is always the top minus the bottom. So it is the limit of x going through 0 and 1 is going from 0 to 1. Okay, it's very clear. And then the top function is x squared. Oh no, I'm sorry. The top function is actually 2x. 2x, because that's the top function. That's the top function. It is 2x minus x squared. Okay, let me erase this and write it again. So it is 2x minus x squared, the top function, minus the bottom function is x squared dx, and then you can simplify. So if you simplify, what are you gonna get? 0 1, you're gonna get 2x minus 2x squared dx. This is easy to integrate, so you're gonna get x squared minus x squared minus 2/3 x cube 1 and a 0, and if you plug in 1 you're gonna get 1 minus 2/3 minus 0, so that means 1/3 unit squared because in area, so the area is 1/3. Okay, so you can see that the problem is not that difficult, but first you need to find the intersection points and then you write the area formula, which is the top minus the bottom curve. It's always the top minus the bottom, otherwise you get a negative value. So you can see that it's not that difficult. Okay, so let's talk about some complicated situations. So we're going to say complex situations, complex cases. So what's a complex case? You can see that there are some curves, they go like that, so they go, one go like that, the other one go like that, so that means it's going to change which one is the top and which one is the bottom. So if that is the case, you have to split the integral at those places. So there's a 1 and then there's a value here, and then there's a value there, and then there's a value there, that's ending value. So what you do, you try to find the area one by one. So split the integral and find the area. So if you say one is fx, the other one is gx, so in this case the area equal is a to d starting with nd value, but you cannot just say fx dx. Now you have to say the absolute value to make sure that you're gonna get positive answers. Absolute value gx, fx minus gx, absolute value dx to get a positive answer. So in other words, but if you know that when you do, because we use this kind of problems earlier when you do the net change formula to find the area or the distance, so it's the same thing. So we can split the integral at those places, so we can write a to b. When you write a to b, it is fx minus gx dx, and then we write b to c, in that case gx minus fx dx, and then you have c to d, in that case it is fx again, so it is fx minus gx. So what you need to do is you need to split the integral into several parts. Okay, so that's what you do, but it is basically the absolute value of the difference of the function. So let's do just one example just to clarify what we are doing here. So we're going to say find the area enclosed by or bounded by, okay, enclosed by curves y equals sin x, y equal cosine x, x equal 0, and x equal pi by 2. Find the area enclosed by curves y equal sin x, y equal cosine x, x equal 0, and x equal pi over 2. So let's draw the graphs and see the situation here. So what we need to go up to pi over 2. So if you look at the cosine graph, it's gonna go like that, and if you look at the sine graph, it's gonna go like that. So so that is pi over 2, and then this is 0. So this is y equal cosine x, start at 1. This is y equals sin x. Good. So now if you look at this area, this situation, so what's going to happen, you can see that there's an area here, and also there's area there, so that they switch the function, so that we need to find what is this value. And we know that the sine and cosine has equal values when x equal pi over 4, so this value is pi over 4. Okay, so the so we can say two curves intersects when sin x equal cosine x. If we divide by cosine x, that's going to give you tan x, which is equal to 1. Tan x equal to 1 means x equal pi over 4. So tan has 1 when x equal pi over 4. So we need some trigonometry here. Okay, so now we have all the limits we need, so then we can write the area now. So the area is again 0 to pi over 2. If you can say cosine x minus sin x absolute value dx, but you actually need to split the integral properly. So it is 0 to pi over 4 was the top function, cosine. So it is cosine x minus sin x, the first one, plus the second one from which is going from pi over 4 to pi over 2. In that case, the sine is the top function, so sin x minus cosine x. Okay, so that's the actual area. So you can finish the integral now. It's a cosine, so it is a sin x, and then minus sine means a cosine x. So you can evaluate that at pi over 4 and 0, plus the second one, sin x means negative cosine x, negative cosine x and negative sin x. This can evaluate at pi over 2 and pi over 4. Okay, so let's plug in the values and simplify. So if you plug in the values and simplify, what do you get? This is 1 over square root 2 sine pi over 4, and the cosine pi over 4 is also 1 over square root 2, and then minus, we're going to plug in the zeros. If you plug in 0, sine 0 is 0, cosine 0 is 1. So that's what you get from the first one, plus from the second one, when you say pi over 2, cosine pi over 2 is 0, so minus 0, minus pi over 2 is minus 1, and then you subtract that, make it become plus. You plug in pi over 4, so you plug in pi over 4, you're going to get 1 over square root 2 plus 1 over square root 2. Okay, so this is what happened. So if you simplify, you're gonna get what do you get? So you have 2 square root 2, so 2 over square root 2 here. Let me square root 2. So there are 2 square root 2. So it is 2 square root 2 and then minus 2. Again, unit squared with area. Okay. So so you can see that the problem is not that difficult, but you want to make sure that you're going to split the integral when they cross each other. Okay. And then also you need to find the intersection points as well. Okay, so we use a little bit of geometry here. Okay, so now the last part. So there is a problem. So what happened, there are some situations when you try and solve. Let's look at this problem. Let's say you have a curve which is going like that, and then there's another curve, let's say, that goes like this. Okay, 2 curves like that. So now let's say your goal is to find the area between these two. So in this situation, if you try to use the earlier method, what's going to happen, you can see the the curve changes, because the first one go all the way like that, but you can see it's the same curve. After that, right after here, it's gonna switch the curves. It's gonna have a new curve now. So after this point, now it's gonna go through a different set of curves. The top and bottom curve change. So in that case, if you just try to integrate along the x direction, that means if you consider x as a variable, it's gonna be difficult. Okay, so so we can say finding area using x variable. X variable is difficult. It's difficult. So what are you going to do? So instead we use the y variable. So instead we use the y variable, because it's going to make the problem much easier, because you can see if you consider the y variable, the curves does not change. It's the same curve all the way. You see that? So it's just the same rectangle, not the same rectangle, but the curve does not change. So but it's not now top bottom, it is right left. Okay, so what you're going to do, you're going to find the right curve, and then you're going to find the left curve, and you subtract, and now these are x coordinate. It's along the x direction. These are x coordinate. So what you want to do is you want to solve for x first, and then integrate not along the x direction, you're going to integrate along the y direction, because now we need the dy instead. See, it's a dy. The gap is dy now. It's not dx anymore. So that means your integral changes. So that means the area is now. So the area is now. So I'm going to call these new limits are c and d. So it's going from c to d, smaller to larger. So that's the d is here. One intersection of the intersections going from c to d. We always got the y in increasing direction, and then what do you want to do to get a positive value again? So we're gonna subtract the larger the smaller. So that means x value of right one subtract x value of left one. Okay, to get a positive answer. Now it's positive or 0, because it's always a larger minus smaller, and then it's a dy now. It's not dx. Okay, so that's the new area formula. So I'm going to erase this one. So let's write the new area formula. So that means you're going to use the y integrals instead of x integral. X integrals are difficult in this situation, because you have to split the integral into two parts, so it's going to make much more difficult. But here there's one thing that you need to do. You have to solve for x. So let's make it clear from one example. So let's do this problem. So the example, so let's say find the area enclosed or bounded, okay, enclosed by the line y equal x minus 1 and the parabola y squared equal 2x plus 6. So you can see it's a parabola not along the x direction, x way, it's the other way. So it's a different parabola. So if you graph them, so what you can do, you can find few points and plot them. So that's the kind of easy way to do these kind of problems. Just try to find a few x values and then find the corresponding y value, and do the same thing with the line. So if you graph it, this is what you get. So if you graph them, so you're gonna get so it's gonna get so that's the parabola. It's gonna go like that. So it's not in the axis is not along parallel to the y-axis anymore. It's parallel to the x-axis. So that's the parabola. And then the line, so let's draw the line. So line is going like this. Okay, so the best thing would be just draw a few points, and then you can find you can connect them, because once you know that it's a line, you just need 2 points. For the parabola you might need like 3 points. Okay, good. So this is okay, so now what's the next thing? So we draw the line here. So the line is y equal x minus 1, parabola is y squared equal 2x plus 6. So so there are two things to do. The first thing is we need to solve for x, because we need to find how the typical rectangle looks like now. So if you draw a typical rectangle, it looks like this. It looks like that. So that means the height is along this way now. That's the height. The width is dy. So we know the dy. That's the width. So it's not dx anymore, it's dy, because we're gonna go top and up and down this time. Okay, so we need to find the corner on the right, and to find the corner on the left. So that means what we're gonna do, we're gonna solve the two curves for x variable. So let's do that. So we're gonna solve for x variable. So if we have let's solve for the right one. So for the right one we have y squared equal 2x plus 6. So that means x equal what is x equal? So we're going to bring it to the other side and divide. So it is y squared over 2 minus 3. Okay, so that's the one on the that's the parabola one. Okay, so that's that. It's the same one, but you can write it like this. So we can call it xl just to make it clear, and the other one is y equal x minus 1. So if you solve for x, so it is y plus 1. This is on the right, so you can call it xr. You don't have to, but you can just call it like that. Okay, so those are the two curves. So you solve for x. Okay, so nothing much, just solve for x. Okay, solve for x. The previous one we solved for y, but it's already given. That's why you don't need this step, because we write y equal function of x is already given there. So yeah, and then if you want, you can write it this one as c to d, the function of y minus g function of y. It's not the same fy from the previous one. So you can see this exercise function of y. They are function of y. It has to be function of y. You have to solve for y before you integrate. So that's one important step. Okay. And then also you need to find the intersection point. So let's say for intersection points, so what happens, you're gonna set them equal. So if you set them equal, you're gonna get y squared over 2 minus 3 equal y plus 1, and if you multiply by 2, you're gonna get y squared minus 2y y squared what do you get? So so you just multiply by 2. Okay, so multiply by 2, so you're gonna get y squared minus 2y minus 4. Okay, yeah. So okay, so in this case actually so it's going to when you multiply minus 6, and then that 2, so you get minus 8. Good. And then these as factors. What are the factors? We have y minus 4, and then y plus 2. So it says that y equal -2 and 4. So those are the y values that we need, so you can mark them. So this is one y value is -2, the other y value is 4. -2 and 4. Okay, so then we can finish the integral. Now we have all the limits and the left function, the right function, so we can write the integral now. So the integral becomes so the area is CD x right minus x left dy. So if you plug in it, so we have -2 to 4. So what is on the right is y plus 1, and what is on the left is 1/2 y squared minus 3. Now you can integrate this one with respect to y, because you see that everything is y. You cannot have an integral in terms of x and you try to integrate with respect to y. You cannot do that. So it has to be same, either y or x. So if you go back to the previous slide, and you can see that the curve on this side is simply x equal y squared over 2 minus 3, and the one on this side is x equal y plus 1. So those are two curves. What you subtract right minus left, always right minus left to get a positive answer. Okay, good. So let's finish the rest of the integral. So that's why so we have the right minus left. Now we can finish the integral. So it is -2 to 4. So we have y minus 1/2 y squared and then plus 4. Okay, so that's the integral. So this is very easy to integrate. We have y squared over 2 minus y 3 over 6 plus 4y. The integral is 4 minus 2. So you're gonna get, if you plug in 4 and 2, so you're gonna get what do you get? So we have 16 over 2 minus 1/6, 64 plus 16. That's the first one. Minus subtract, you're gonna get 2 plus 4/3 minus 8, and if you simplify, you end up getting 18 unit squared. Okay, so these are the kind of typical area problems, and as we discussed before, you can see that if you try to do it using the x variable, what's going to happen, you have to split the integral into two parts, because one integral doesn't work because they change the curve. So they in the first part you have these two curves, and the second part you have two different curves here. So that means it's going to make it complicated. So you can have one integral, but if you try to integrate with respect to y, what's going to happen now, those two curves stay the same if you try to integrate in the other way, in the y direction. So that's the benefit of switching the integral, because just doing one integral, now you can find the area. Okay, so we're going to practice more problems in the homework. Okay, so this is the end of the area problems. Thank you.